Hi, my name is Doug Sparks, and I'm going to be talking about how micro and nanotechnology is being used in the field of inertial confinement nuclear fusion. Now, what is required to trigger nuclear fusion, and how has this been done in the past? Well, we're all aware of the sun as a source of nuclear fusion, and it utilizes gravitational confinement to push together the hydrogen atoms at the core of the sun to initiate fusion. Of course, that's how we generate heat and light for Earth. Um, so that's something we see every day. Now, inertial confinement diffusion is a man-made uh, approach to accomplishing the same thing. In the 1930s, this was first demonstrated with particle accelerators, accelerating deuterium uh, atoms together and fusing them to form helium. We're all well aware of the hydrogen bomb, the fission explosion that is used to trigger that. That was developed in the 1950s. And then most recently, some very interesting work has been done at Lawrence Livermore National Labs on lasers, using multiple lasers to compress and confine deuterium and tritium together for this inertial confinement. And inertial again means moving these things together, and inertially they keep going and fuse together. Now, the Lawrence Livermore National Labs uses 192 lasers to trigger this fusion event. The laser energy and resulting X-rays that are produced accelerates the deuterium and tritium together, causing fusion, releasing a lot of energy, as well as some helium and neutrons. And there was a really, I guess, record-breaking development in December of last year in which they got more energy out of the vacuum chamber than was put in. Again, and this was repeated in July of 2023. For those of you who have watched the media, have seen this, here's some images from a CBS report that was done early this year, 2023. Just shows some of the elements that were used. You've got this huge vacuum chamber with the laser, in the laser ignition facility. You have a tiny diamond sphere. It's in the palm of this person's hand. And that's where the fuel pellet, that's essentially the fuel pellet where the tritium and deuterium ice is kept. And this little sphere is made using micromachining techniques. It starts off as a silicon sphere itself. It's coated with diamond or carbon. The silicon is etched and removed. So there's a lot of techniques that I'm going to really focus on in this talk. To get that fuel in, they actually have to attach a tiny microtube. It's smaller than a hair. It's kind of the fluidic port to get that deuterium and tritium vapor in there to freeze up on the insides of that diamond tube. And then the sphere itself is put in this hull room, which is kind of an ignition chamber holder that's inserted into the vacuum chamber. Now, the fuel pellet holder is it's a gold and copper basically fixture that holds the fuel pellet. Of course, this fuel pellet is cryogenically manipulated. It's very cold because the deuterium and tritium vapor has to be in the form of ice coating the insides of this diamond sphere, and then the lasers hit the hull room, which is again copper and gold. That causes X-rays to be generated, and that compresses, implodes the fuel pellet, which triggers the fusion event. In the bottom right there shows the hull room after the ignition event, so you can see how the metal was kind of exploded from the force of the fusion event. Now, silicon micromachining, also known as MEMS, was key to this fusion advance. So what is MEMS? It stands for micro electromechanical systems. It can also be micro nano mechanical systems. It's most often used for sensors and actuators. It's a kind of a subset of semiconductor processing. Typically it's using silicon as the main material. Or it may also use glass, it may also use metals. These things are three-dimensional chips that can actually move, so there's moving parts to them. And they're found in everything, in modern life: smartphones, smartwatches, automobiles, you name it. If it has a microsensor or a micro actuator, it probably has a MEMS chip in there. Now, to understand how the silicon spheres and the diamond shells are made, you've got to kind of understand how silicon wafers are made. And of course, silicon wafers are even more pervasive than MEMS, because these are used to make the computer chips that are in our laptops, as well as our phones, and anything else that is electronically actuated or monitored. So you basically take with sand, you start with sand, silicon dioxide, you remove the oxygen, you got single crystal silicon, you've got to melt that down, you've got to pull an ingot, you slice this with a saw into what's called a wafer. It's like a little disc-shaped platter. Then you have to polish the surface of this silicon wafer prior to going into what's called a wafer fabrication facility. And then you'll do things like coat it with metals, oxides, etch it, and pattern things. So that's how a silicon chip is born. To make this deuterium or tritium fuel pellet, instead of having flat discs, you've got to make almost a silicon ball bearing, a small silicon sphere. So you're kind of merging manufacturing techniques used for silicon computer chips with stainless steel or steel spheres or ball bearings. So by merging these two mechanical processes together, you can form the first part in the fuel pellet for the fusion, inertial confinement fusion device. One of the steps that are used in polishing wafer, it's called chemical mechanical polishing. You're getting nanometer surface smoothness, polishing this better than most mirrors would ever be polished. You use a combination of what's called a slurry. So it's a fine grit coupled with some reactive chemicals that actually etch the silicon surface. So you're polishing this, polishing it flat. That's how you make a silicon wafer. Now this kind of tooling has been modified to polish these silicon spheres, and that's shown on the right. You've got this grinding disc on the top, which is the polishing pad. You've got some colloidal slurry materials with abrasive materials and chemicals that etch silicon. And then you've got a groove track where you put the silicon spheres into, and you just polish away, almost like a rock polisher in a way of thinking. Now here's the rest of the steps for making these fuel pellets. Again, start with a thick silicon wafer, dice it into cubes, round off the corners, polish a sphere. You then coat that sphere with a diamond shell. You've got to etch a single tiny channel into that diamond shell. And the reason you do that is shown next, because next you have to etch out the silicon. You've got to remove the silicon and leave behind a hollow diamond sphere. You then attach this tiny microtube, which is shown in a picture there in the far right, to the sphere, and you can imagine how tedious that operation must be. You then, the deuterium tritium vapor enters the sphere, the interior of the sphere, through this microtube, freezes around the outer edges to form the fuel pellet. And I list some references down below as you can dig into this in more detail. So the one interesting step is coating this polished silicon sphere with diamond. So just like we had to have a special piece of tooling to polish the silicon spheres, you have to have a special piece of tooling to uniformly coat the spheres with diamond. And this is done with a process called chemical vapor deposition. Again, this borrows and leverages tooling that was made for coating silicon wafers, which is shown on the far right. This is called a planetary rotating deposition system. And again, to make the spheres uniformly coated, while you're depositing the diamond film, you've got to move and you've got to rotate these balls so the material is being sprayed or coated onto the exterior surface. And again, this leverages machine tool coating, diamond machine tool coating. It leverages diamond and graphene film deposition for semiconductor devices, because diamond and graphene or carbon are being used in advanced semiconductor devices as well. So this type of know-how in the semiconductor industry was leveraged to make the shell that coats the silicon sphere. Another really challenging step in fabricating the fuel pellet is etching away the silicon. We have decades of experience in etching silicon, both for integrated circuit fabrication and MEMS devices. I mean, most MEMS devices have to have silicon etched, and there's some pictures that just show some examples of how silicon can be etched to make a MEMS device. Plasma etching can be used to etch very deep channels, just like the channel that needs to be etched in that carbon shell. After you etch down into the silicon, you got to etch away the interior of that sphere of silicon, which is a challenge, and you got to get that gas or reactant products out that very thin channel. That is a big developmental effort that had to be undertaken. So we've talked about a lot of interesting technology just to make a fuel pellet. Is this laser-based inertial confinement a path to carbon-free green energy? That's what everyone hopes, and that's what we've all been talking about for 70 years, that we could just take water from the ocean, use fusion technology to create energy. That's the goal. And when you think about this, I was struck with the analogy with coal, how we generate heat, light, electricity with coal. And the reason I thought of that was, we're using carbon spheres to hold this deuterium and tritium. In my mind, it was kind of like a little chunk of coal being blasted with lasers. Now, of course, in the laser ignition process, we're not generating carbon dioxide, so it's not going to generate a greenhouse gas, but still the analogy is there. Look at how long it took us to discover, first of all, that coal could be used for heat. That was 2,000 to 3,000 years ago, back in China, Britain, Greece, Rome. Coal was used. It was thrown in the campfires. It was used as a supplement for wood. It was, accidentally discovered. But really, until electric and steam-powered motors were invented during the Industrial Revolution, it basically was kind of languished as a novel way to heat your fire. And in my analogy, I see the laser ignition project is almost at the coal campfire stage, because we've only done 2 ignitions in the last 6 months. We've thrown the carbon sphere filled with deuterium, zapped it with lasers in the big laser fire, and generated more electricity in that vacuum chamber than we put into it. So just like with coal, you have to go through a progression of technical development and commercialization. So, the first steam engines were loaded with shovels. With the advent of electric generators or dynamos, they used these steam engines to make electricity back in the 1880s. The first steam turbine was only 1% efficient. Now we crush coal into fine pellets. We use conveyor belts to feed it into the plant, and we're up to 30 to 40% efficiency. But again, centuries, if not millennia, of progress was needed to get to the place where coal could be used to power an industrial society. And it's been estimated by the scientists at Lawrence Livermore Lab that you're going to need to do 900,000 fusion ignitions with the lasers a day to hook into the power grid. So 900,000 per day. That almost seems impossible. And I thought that, that's not practical. But then I came across another semiconductor related process, which is called extreme ultraviolet lithography tools. ASML, they're the world's leader, probably the biggest seller of semiconductor fabrication equipment in the world. They're in the Netherlands. And their most advanced system actually uses laser ablation, laser vaporization of tin droplets to create the 13.5 nanometer light source used in these lithographic tools. To do that, they have to hit tin beads with lasers, two lasers. One laser creates the shape and the other one blasts it, or vaporizes it. They do this 50,000 times a second. There's 50,000 tin beads shot into a vacuum chamber, hit by lasers every second. So when you look at that, you think, well, 900,000 shots per day isn't crazy. It's already being done on this ASML tool. Now again, this tool is a $200 to $300 million tool, and it took them a decade to develop. But it shows that if you really focus your attention on a problem, you can come up with a solution. And we've done that. We've been able to rapidly hit metallic beads 50,000 times a second all around the world in wafer fabs. So I think, the underlying technology is there. Of course, it's going to have to be adapted for 192 lasers instead of 2. And you're going to have to be able to make these fuel pellets. They're a little bit more difficult to make than just squirting out liquid tin into a vacuum. So there are barriers to overcome. The biggest barrier is increasing the fusion gain, because while there was a positive gain out of the vacuum chamber, it took over 100x greater amount of energy to power those lasers to shoot the laser beams into the vacuum chamber. So we're by no means creating more energy than was used at Lawrence Livermore Lab. We're going to have to shrink the fuel pellets. Maybe we can leverage semiconductor manufacturing to do this. We certainly can mass produce billions of silicon chips a year. Perhaps we can somehow leverage that technology and manufacturing expertise to produce billions of fuel pellets. And then the rapid loading, 900,000 pellets per day to feed into that laser inertial confinement system. That's going to be a challenge, but I think ASML has shown us a path to do that. You're going to have to do that without destroying, the sample holder every time. There's going to be carbon buildup on the walls of the laser confinement system, so you don't want to block the laser light or reduce efficiency. So there's going to have to be a whole number of technical issues surrounding that part of the problem. And I would say, although we are vaporizing the carbon with the lasers, we're not creating CO2. So I think there is a path to overcoming these barriers, but it's still going to take a lot of work. Thanks.